Hi everyone, I'm Connor from MWR. I'm the head of mobile security, and today I want to talk to you about, well, TLS amongst other things. So as you can see, the slide is titled Terrible Layered Security, and we'll be discussing some ways where people can essentially try and implement TLS but make mistakes, and what the consequences of these things are. With me, I have Andre, who's just going to do a brief introduction of himself.
So, hi everyone, my name is Andre. I'm also a MobSec consultant at MWR CyberSec. I joined about a year ago, but in that time I've still bared witness to terrible horrors beyond imagination, so I'm going to share my experiences as well.
So, at the end of the day, this talk is about certificate chain validation, certificate pinning, domain name verification, and then as an added little extra, we've got custom cryptography. Before we get into the technical details of this talk, I'd really just like to talk about some real-world examples of how these things have gone really badly. The first example here is a paper titled Spinner, the semi-automatic detection of pinning without hostname verification. Now, we'll get into the nitty-gritty details of this paper in a bit, but at the end of the day, the really terrifying thing here is large companies were found to have their mobile applications not even do chain validation, i.e. they could be man-in-the-middle using a self-signed certificate. So that is incredibly scary. We have names like HSBC here, for example. The next thing that we're going to discuss is CVE 2018-8970, and this is a vulnerability that was identified in implementations of Boring SSL as well as Libre SSL, which led to what I would dare call a trivial man-in-the-middle attack. Again, we'll get into the nitty-gritty of this a little bit later, but I just wanted to kind of prepare you guys for what's to come. And so with that, I'm going to hand over to Andre, and I will catch you guys in a bit.
Thank you, Connor. All right, so I'll be going over the first point, which is certificate chain validation. Before we actually get into the nitty-gritties of it, let's just go from an example that we're a bit more familiar with. So when you use a browser to navigate the internet, it will perform a number of certificate validation checks. And if any of these checks fail, it will obviously present you an error. This is good and all, but we often take this for granted. It's a feature we commonly see, but is it actually implemented everywhere? So often on mobile applications or their clients, we'll see that the implementation details are often left to the developer. And as not all developers are familiar with, the intricacies of how a certificate should be verified, this leaves a lot of room for error. Consequently, it's not unusual to see some errors with custom implementations. But then we have to ask, what is a good implementation? How do we actually get to it? So before I jump into code examples, let's just cover the basics. So certificate validation is the process of checking whether or not we have, whether or not we trust the certificate that's being issued to us. And as I mentioned, on browsers, this happens mostly without thought. On mobile applications, we have more control of the certificate validation process, and hence this becomes a more prevalent feature that we have to keep mind of. The process starts with us receiving a certificate or chain of certificates. This is normally presented as an array, and I've sort of somewhat highlighted that there loosely. You can somewhat see it's an array. One of the certificates will be the leaf certificate, which is represented, one of the certificates is the leaf certificate, which represents the server we're connecting to. And then the others are normally intermediaries. In this example here, we've got one that's a root certificate, though this might not always be presented as part of the chain. So the job of a certificate verification function is to ensure that the chain is valid and that the certificates verify one another, and that the end certificate is actually signed by a root CA that our device trusts. So that's all good and well, but a visual example might help describe that process a little bit better. So let's take Let's Encrypt. Let's Encrypt has two root CA certificates, namely ISRG root X1 and X2. These are followed by intermediary certificates, which are R10, R11, E5, and E6. The following certificates at the bottom there, you'll notice, are the ones that we actually issue to clients. So we can see on the right-hand side of the screen that Android 12, or at least the Android 12 device we were using, imports the ISRG root 1 certificate as part of its system certificates. Now, those of you with a keen eye might also notice, well, hang on, that's a little bit weird. We don't import the X2 certificate. What's going on there? That's a whole nother discussion, but the important part is that you do see that the X1 certificate is included in the list of trusted system certificates. So if an application receives a certificate chain with both the R10 intermediary certificate and the client's leaf certificate, the application will have to verify the leaf certificate has been signed by the R10 cert, and that the R10 cert has been signed by the X1 cert. All right, so now that we've got a little bit of a clearer picture, let's look at some code examples. I should just note that with chain validation, a lot of things can go wrong, so we're going to be teaching sort of, or going through these slides sort of from the perspective of how things can go wrong. The examples I'll be demonstrating will mostly be Java and Kotlin, though Connor will jump into other programming languages at a later stage. And yeah, I just want to make explicitly clear this code is just for demonstration purposes and should not be considered authoritative. All right, so in our first example, we have an SSL context object that is used to establish a connection. You can see it sort of towards the middle there. We then make use of a custom trust manager, which you can see sort of at the top, and that's used to handle certificate validation. So, as I've mentioned numerous times now, certificate validation is a difficult and highly error-prone process. So we have to ask ourselves, what's wrong with this implementation? Now, that question is going to be a little bit rhetorical because time concerns, so I'm just going to jump straight to the solution. So if we ignore all of the rest of the code and focus on the trust manager implementation, we can see that the check server trusted method, as well as the other two methods above it, don't actually do anything. The check server trusted method is supposed to validate a certificate chain, and if it discovers anything wrong, it's supposed to raise an exception. But in this example, it just simply returns, performing no actions. So consequently, this function will accept any certificate passed to it. This means that it would be possible for an attacker to present their own self-signed certificate and man in the middle of the application. You can see at the bottom there, we're making a request. Sorry for those that are sitting a little bit further away. But we're making a request to selfsigned.badssl.com, which is designed to present a self-signed certificate. This is the type of certificate that we would normally expect an attacker to present when they're man-in-the-middling an application, for instance, using Burp Suite. But now, if we run this code, we can see that a successful connection is made with a 200 OK response, and that the certificate has been accepted. So you might think, okay, this is all good, but it's an unrealistic example. Who in their right mind is going to do this? But we have actually come across implementations like this in the past. Regardless, though, how can we improve? Well, we can start by providing an implementation. So in this new code snippet, we've provided a bit of a naive example of how one might go about verifying certificates passed in the chain parameter. There are numerous errors with the above, especially considering there's a lot of checks that aren't being performed. But we're going to focus primarily on the logic error here. So again, it's going to be somewhat of a rhetorical question due to time constraints, but can anyone sort of identify the major logical error being performed here? And I should mention that the chain.verify function in the middle does throw an exception if the chain is not valid. So that's not the issue. If I move on to the solution, again, ignoring the fact that we don't actually do any other validation checks, we can notice that the for loop here will attempt to follow the chain and validate each of the certificates. It does this by looking at the certificate ahead in the chain, obtaining its public key, and then using this to verify the current certificate in the loop. So yeah, this loop inherently requires at least two certificates be present in the chain parameter, as otherwise, how's it actually going to go ahead and look ahead in the loop, right? So that's great, but what happens if we pass a single certificate? All of a sudden, there's nothing to look ahead in the loop to see, to retrieve a public key from, and this loop is skipped, which means that no validation checks are being performed, and thus meaning that, again, a single self-signed certificate will result in a bypass of this function. So again, if we run the application, we can notice that we receive a 200 OK response from the server, and it trusts the single self-signed certificate that we passed it, which can be seen Sorry again if the font's a bit small, but it can be seen in our debugger, and it can be seen within Firefox. All right, so basically just as a recap for the chain validation component, we've gone over an example where chain validation performs no checks, and again, this does happen. It mostly happens because developers are running into some sort of chain validation error. They're busy on working on some other functionality of an application. They don't have time to deal with it. Just disable all the checks. And we've also gone over an example with some logic errors that would be bypassable with a single self-signed certificate, which again, it is something that crops up in custom implementations. So how do we fix this? We could spend hours ensuring that we've encapsulated every edge case and logic flaw, and we could ensure that we've correctly validated our certificates and have made sure that they're signed by a system-trusted CA. But this work has largely already been done for us. So going back to our original code example, all we can do is simply replace the custom trust manager object with a null value, which when initializing the SSL context object itself. So this null value will indicate that the default trust manager implementation will be used, which does handle many of the edge cases we face. But it will also be implemented in a much more secure manner than what the average developer, whose main focus is on developing some other functionality, can do. Yeah, and at least as well, again, a normal developer's main concern is developing some other functionality and not dealing with some pesky certificate error. So yeah, with this implementation, the request to the self-signed.badssl.com domain will fail with an error message, as it should on self-signed certificates. We've seen a number of custom implementations through the assessments we've performed, and some of these, like I mentioned, did the same thing as the first example, and others did have bypasses that were similar or replicable to the second logic flaw that I demonstrated. So yeah, these are, again, as I mentioned, mostly just the result of developers trying to avoid certificate validation errors, but it also occurs when developers are trying to implement additional controls, and this particularly crops up with certificate pinning. So, what is certificate pinning? Well, oh yeah, and also, do we actually need it if we perform chain validation? So, while it's true that performing certificate chain validation does secure communications to an extent, it's actually very integral. There are a few additional defense in depth measures that can help make sure that our application is more secure. So certificate pinning is one such example. It is a measure that protects against a certificate authority being compromised and then issuing malicious certificates that can then be used to man in the middle of our applications. So we'll see how this works with a few examples. So as usual, before we jump into the code, let's just discuss how the mechanism works briefly. So certificate pinning is the process of selecting a certificate in the chain that you always expect to see. For instance, in this diagram, it's the orange highlighted block. And then once we've picked out the certificate that we expect to see, we can maybe, for instance, hard code this value in the application and make a point to check that it's present in the chain that we receive. If this value does not exist, then we can reasonably assume that we've received a chain that doesn't quite make sense, and then we can close the connection. So, how does it work in code? It follows a similar approach to what we've seen before with the normal chain validation. As usual, none of this code should be considered authoritative. These are just for demonstration purposes. So in the example I've listed there, we've implemented a very basic version of certificate pinning. More specifically, we've pinned an intermediary certificate using the chain1 parameter. It's sort of right, or the second item in the chain array. So it's sort of 3 lines in. We're making, again, the assumption that, in this case at least, that the certificate will always be in the second position. And then, as usual, we should ask ourselves, what could go wrong? So if I just jump directly to the solution, the first thing that we should be able to identify of course, is that we haven't actually implemented chain validation. And that is because we're using the same check server trusted method as before. So chain validation and certificate pinning are implemented within the same function, which often causes a lot of confusion. So with the current logic, it would be sufficient to submit a chain with an intermediary certificate that contains a public key that we've pinned, and then we can otherwise do whatever we want with the other certificates. And so yeah, why is this important? Well, again, it allows us to man in the middle of the application. So let's go through it step by step and see how the application can be man in the middle. When we run our program, we'll receive a certificate chain in the chain parameter as mentioned previously. Yeah. So the chain parameter, if we were to draw it out in a diagram, it might look as follows. We've seen this a number of times. It's an array. We've got values 0, 1, 2, and 3. We have a leaf certificate in this case, 2 intermediary certificates, and a root certificate. So now if we move on to the if statement, or the if code block in our code, we can see that this code block will throw an exception, and it will terminate our connection if the pinned certificate doesn't match the received intermediary certificate we're expecting in the second array position. So as a visual aid, let's say that we've pinned a certificate that's referring to a public key in the first intermediary certificate, so basically number 1 there. That means that the certificate's public key must be present in the chain array in order for validation checks to succeed. So as a malicious user, we may have knowledge about this process because we may have reverse engineered the application. And in order to prepare for our attack, we can start by generating our own malicious certificate chain that we control. I should note that in these cases, we were using the debugger and sort of mashing in extra certificates in. But in most cases, you would need to actually have a server that can, will agreeably actually serve that certificate chain. All right, so again, since we as the attacker have control, we're able to manipulate the chain's contents. So therefore, we can insert a malicious certificate and with a public key that matches the one that's being checked for in the code. So the red portion there sort of appears a little bit orange, but maybe that's just my perspective. So yeah, it shows how we've inserted an extra certificate that shows how the chain is being manipulated. And now with this additional modified chain, we can pass it to the previously used check server trusted method, and it will trust this chain. And that is because it fulfills the basic prerequisite of having a certificate with the correct public key. So under normal circumstances, I should mention that this would fail because of chain validation. And this is because, again, our injected certificate may reference a completely different leaf certificate. If we start from the top, or at least from point 2, the public key under the certificate number 2 would not verify the signature of certificate number 1. This is because certificate number 2 was not used to actually generate certificate number 1. And likewise with certificate 0, certificate 0 would not be verified since certificate 1 would not have the correct public key to verify its signature. So if chain validation were to be performed, this forged chain would immediately be rejected. But again, it just so happens that in implementing certificate pinning, developers will often forego chain validation logic because they occur within the same function. So let's take a look at another example where we've attempted to fix this issue. So this builds on the previous slide. Again, I apologize for the small font. But I'll just describe it. So basically here we have a function that's performing both chain validation and certificate pinning. So the top block is calling the default certificate chain validation implementation, and the bottom block is doing the certificate pinning that we saw previously. However, there is a logic flaw with this code. So jumping right to the reason or what it is, we can see that we've introduced an is trusted or is chain trusted variable right at the top. It's highlighted throughout the code block example. And there is, right at the bottom, there's an if statement that is used to determine whether or not an exception should actually be raised. So we can see that an exception is thrown when the default chain validation error occurs with the catch statement, because our normal chain validation occurs in a try-catch statement. And in the catch statement, we have the is trusted chain value being set to false. So the chain validation part of this code works as expected. However, the same logic is applied to the certificate pinning portion of code. So again, if the certificate is actually valid, the is chain trusted variable is then set to true. So because we're sort of assigning values to this variable constantly, it means that chain validation could be invalid, right? We could have an invalid chain. But if our certificate, if it finds the correct pin certificate, it means, okay, great, this is trusted chain and we can move on. So this is similar to our previous example in that, again, we can just ignore chain validation completely. So again, that was sort of a bit of a naive example, but it shows how implementations do often have these weird logic bypasses. And again, if you're a developer who, again, is focusing on something else, you're not really there to go and validate certificates, it's easy for these logic flaws to slip through. So just to summarize what we've covered, we've gone over certificate pinning, or an example that doesn't implement chain validation, and we've stepped through the entire process. We've then proceeded to also talk about another example that shows how even if we do attempt to implement checks, logic flaws may exist. Again, this code gets complicated, and it's not always clear where those logic flaws might be. So again, how do we fix this? Again, this code should not be taken as an authoritative example. It's just for demonstration. But if we want to perform, in general, what we want to do is we want to perform the default certificate validation checks, as we did before. And we want to add our certificate pinning checks as well afterwards, again, as was shown before. However, we should not block either of them from raising an exception. So that shouldn't occur in the certificate chain validation portion of code, shouldn't occur in the certificate pinning portion of code. So again, this is just an example. Please do not implement this in your projects. All right, so as a summary, certificate pinning is a defense in depth control. Its implementation often leads to vulnerabilities in chain validation, and this is particularly because both chain validation and certificate pinning rely on the check server trusted method, at least in Java. And it is generally recommended that we call our default, the default check server trusted implementation and add any of our additional checks afterwards. On Android, there is a network security config.xml file that can be used to make the process of adding or make the process of certificate pinning easier. There's also a further discussion to be had about where do we actually pin on the chain. But we'll leave that out of scope for this talk now and move on to another important control. So I'll hand over to Connor now, who's going to discuss an extra control which might not be thought of as often as it should. Cool.
All right, thank you, Andre. So the next control that we're going to talk about is called hostname verification. So traditionally, when you do chain validation, the only thing you really know about this chain that's been sent back to you is that we can trust the leaf certificate. We don't, in fact, know that the host that we're talking to is the host that we intended to talk to. So the process of hostname verification is, in reality, really simple. If you look at the screen there, you can see at the top we've got a host called bastion.conspox.com, and at the bottom we've got the certificate that has a common name of bastion.conspox.com. And what we've just done is essentially the process of hostname verification. We've ensured that the common name in the certificate matches the physical domain name that we connected to. Now, this is incredibly important because if you don't do hostname verification, you are vulnerable to a trivial man-in-the-middle attack whereby any certificate in the world that is trusted by a certificate authority and that certificate authority is on a device can be used to man-in-the-middle your connection. So if this mistake was made by something like a bank, for example, I could man-in-the-middle the connection by simply using the certificate that I use for my blog. Really scary stuff, right? So you might be surprised to hear that a lot of stacks don't actually treat host name verification as a part of chain validation. I would argue that both these things are absolutely integral to making sure that we can trust the TLS channel. So it is very surprising to hear that Java, for example, does not perform host name verification out of the box, whereas something like Go, Python, and C# do perform that. So let's jump straight into an example. Here we can see we're connecting to a host called wrong.host.badssl.com, and at the end of the day, this is just a raw TLS socket that is creating an HTTP request, as we can see there. We're just sending a GET, and we've got a try catch at the end to let us know if anything went wrong. Now, you're welcome to connect to this host on your phone, on your laptop, should you have it with you. What you'll see immediately is an error telling you that the certificate common name is considered invalid. Now, this is because badssl.com serves a wildcard certificate for, well, wildcard.badssl.com, but the common name that we're trying to connect to is wrong.host.badssl.com. So that mismatch is the thing that's causing this certificate warning. However, if we go back to our Java implementation, we can see that even though there's a mismatch in the common name, the response is returned. Again, this just opens you up to a very trivial man-in-the-middle attack. What's interesting here is just how different stacks treat something like hostname verification. So you'll see that a browser, for example, will give you a warning. However, if we look at something like a HTTP client, it also provides you with a warning. You can see at the bottom there, Kul is complaining about the no alternative certificate subject name matches the target host name. It's the exact same error, and we're expecting to see this with HTTP clients. When we move to TLS clients, as with the previous example, however, you're not necessarily guaranteed that domain name verification is actually being performed. So let's look at a very naive implementation. We can assume that chain validation is being done. However, all this is really doing is fetching the common name from the leave certificate and checking if it contains the keyword google.com. Turns out that something that passes this constraint is actually really easy to come up with. We can go with something as simple as google.com.attacker.com, which would be considered valid and would again allow you to man in the middle of this connection. So a safer implementation is actually incredibly trivial, but before we get to that, I just want to reiterate what Andre was saying. Whenever we're trying to increase these controls on our TLS connections, or, God forbid, relax them, we have to implement this check server trusted mechanism. And unfortunately, again, it's the exact same place where chain validation, certificate pinning, and domain name validation has to occur, and this confusion can lead to vulnerabilities in the software that we test. So firstly, there's the interface. We don't really care about check client trusted or get accepted issuers in this case. When you're just doing a normal TLS connection, the most important method is check server trusted. If we continue, we're going to essentially just have a look at the two different blocks here. So this is a trick that I learned from CSI. It's called zoom and enhance. And as you can see, we're just checking whether or not the leave certificate is a literal match against wildcard.badssl.com. Just ignore the fact that the host name changed there from out under you. If we go to the next example, so the second critical part of ensuring that this connection can be trusted is performing chain validation. So this implementation just essentially gets all of the default trust managers on the device and runs the check server trusted mechanism with the chain. If an exception is thrown, it'll be bubbled up to the original mechanism, and the connection will be killed if there's anything wrong with the chain. So let's look at a safe implementation for Golang, and there's a very good reason why I picked this one. So firstly at the top, firstly, we can see that the code is a lot more simple, which is a really good thing in my mind. So we start by specifying the physical domain name that we want to connect to, google.com, and the port. Then we create a TLS config option for which we set the SNI, or server name indicator, that just tells that receiving server what host am I actually trying to talk to. And you'll see that this is set to facebook.com. So this very trivial program emulates what an attacker might do to try and man-in-the-middle Google using a valid certificate from Facebook. And if you've been reading the news lately, this is not such a far-fetched example. When we run this example, we get an error that says, failed to verify the certificate or the X509 certificate. And herein lies the really important part. The Golang implementation out of the box performs hostname verification, not deferring or delegating it to the calling application, which is secure by design and which is what we essentially want to go for. We're going to come back to this example because it becomes important when talking about one of the real-world examples. So this is the research that I was talking about earlier called Spinner, the semi-automatic detection of pinning without host name verification. Really some phenomenal research that was done. There's a tool that accompanies this that attempts to essentially test whether or not a mobile application is vulnerable to this kind of attack. But let's maybe just take a step back and first talk about what the constraints are, what we need to be able to man in the middle a connection that makes use of certificate pinning, chain validation, but does not perform host name verification. So we've got two pretty decent constraints there. The first one is that you need a valid certificate. I mean, anyone can go to Lect and Encrypt and just get a certificate for any domain that they want to. So that's done fairly easily. The second constraint is that somewhere in your chain, there must be a public key that matches what's been hard-coded in the application. Now, that is a fairly large task. You're not going to get the exact same chain, but it turns out what you can do, if you look at the top at HSBC, they use Symantec, they pin one of the Symantec certificates. So what you could do is go to the same issuer, ask for a certificate, and essentially send up a prayer and just hope that you happen to receive a chain that happens to contain the same public key. And if you do, for the low, low price of $1,000, you can now man in the middle HSBC's applications. I think the scarier part, so that was already a feat of itself, but the scarier part here is that while doing this phenomenal research, these guys figured out that there are a bunch of apps on the App Store that just accept self-signed certificates. So imagine you went through all this effort to do this research, and you just didn't need to do any of it at the end of the day. So really would highly encourage you guys, scan the QR code if you want to go read the paper. It is incredible. The tool itself is also linked in the paper. A really good thing to kind of grasp with these concepts and understand them a little bit better. So moving on to CVE 2018-8970, I mentioned that this was a vulnerability in Boring SSL and LibreSSL. This affected not Chrome, although Chrome does use Boring SSL, so it was almost very, very scary. But it did affect OpenBSD, Python, Alpine, and either Postgres or MariaDB. I can't remember exactly now. But what essentially happened is we need to first understand how do we use OpenSSL as a caller of that library. So we can see that we have this mechanism called X509 verify parameter set one host, which is a mouthful, but it essentially takes three parameters. The first one is some kind of magic context object, and we honestly couldn't care less about it. The second parameter is the host that we're trying to validate. So does the common name match whatever is contained within verify host? And the third one is a size parameter, and this is where the interesting bit comes into play. So the authors of Boring SSL wanted to create an OpenSSL implementation that is, or at least different goals compared to the original OpenSSL implementation. So they have their own new interface that you can use, and this is really important. This new interface does perform hostname verification out of the box, but the older one, so the interface that's compatible with OpenSSL, it's the same interface but a different implementation, does not perform hostname verification unless you opt in. And that's also true for OpenSSL itself. If you just use it out of the box, you're not doing hostname verification, you need to opt in to hostname verification. So let's just take a very brief look at what this function looks like, right? We talked about the magic context object, we don't care. We talked about the verify host parameter. The size parameter being 0 might be a little bit strange to the audience. At the end of the day, what this is just a C-string, a character array of a bunch of bytes that just ends with a null terminator, and that's how we know how big this particular host is, or at least the string that represents the host. So OpenSSL supports multiple, let's call it, calling conventions for the argument's sake, whereby you can use a C-string-like call, as we're doing here, where the runtime is responsible for figuring out how big the actual object is, or we can specify the object size ahead of time, so 5 bytes, for example. Now, the Boring SSL authors are not fans of the C-string calling convention, the idea that the caller can pass in some kind of object that has an unbounded size and we have no idea what that size is, well, frankly, a bad idea. So they never implemented or never intended to implement support for this particular interface inside of Boring SSL. So let's just dig a little bit deeper. What you can see there at the bottom is that if the name length parameter is set to 0 or the name parameter itself is null, we immediately return 1. Now the implication of this, just for anyone who's not aware, in C or C++, anything other than 0 is considered as true and 0 itself is considered as false. So when you run this function and you use the C-string calling convention, it would immediately return without raising an error whilst indicating that hostname verification was successful. And what I meant by how this leads to a trivial man-in-the-middle attack is that essentially now all we can do is the exact same attack that I discussed earlier, where we take a certificate, blog.consbox.com, for example, and we use that to man in the middle something like a bank's mobile application. Now, again, this impacted OpenBSD, Alpine, Python, a bunch of software, not Chrome, luckily. But I'm sure you can see how something like this could be incredibly impactful. So the fix here is actually very interesting. I suppose the vulnerability was introduced by 2 lines of code, and it's only apt that the fix is also just 2 lines of code. So all we do is we just check if the name length parameter is set to 0 and a parameter is actually passed through, we determine the size of this parameter, and the little bit of code at the bottom that's still responsible for introducing the vulnerability is never executed, and thus this was patched with this is literally the entire commit. It was just 2 lines of code. What is interesting here, before I get to that slide, while doing research, I came across one of the committers called Adam Langley. So I sent him an email asking 2 questions. Is it normal for TLS clients to, let's say, not perform hostname verification? And secondly, why would the Go implementation be so fundamentally different compared to the Java implementation? And we've come full circle because the answer is actually quite simple. It's older software. At the end of the day, the Java implementation is much older than something like the Golang implementation. So he did confirm that historically, chain validation was performed by your TLS client, but was deferred to the calling application. As we'll see in a bit, recently that's changed. It's for any modern library. The idea is that the library will be responsible for handling both chain validation and hostname verification, seeing as these things are so critically intertwined. So the second question that I asked was, why would the Golang implementation be so fundamentally different from the Java implementation? And he answered in a very funny way. He said, well, I don't think I was the first person to change this implementation to behave in that way. At that point, I thought, maybe I'd bitten off a bit more than I can chew here, because I had no idea who Adam Langley actually was. So just to put it into perspective, he is one of 2 people who committed to a fix for the Heartbleed vulnerability in OpenSSL. He's worked on Google Chrome's networking stack as well as Google's HTTPS infrastructure, and he is also the author of Golang's entire TLS package, just per chance. So the reason that Go actually performs hostname verification out of the box with the standard library was a direct result of this vulnerability. It's a decision that they made to say that, look, this doesn't seem like a good idea to defer it to the calling application, so let's learn from our mistakes. Let's rather do this for the developers, which I think is excellent. It shows how, as an industry, a tech industry, we can grow and can learn from our mistakes. I do want to highlight, Dominic had this excellent point about community. I do think it's really amazing that we work in an industry where I can reach out to someone who has, or is arguably such a behemoth. I would guess that everyone sitting in this room has at some point used software that relies on something written by someone like Adam Langley. So I just think it's incredibly amazing that you can reach out to someone like that and get an answer. And it's not been the only scenario where I've had instances of something like that happen. So as a summary, if you fail to perform hostname validation, it invalidates any security that you actually get from TLS, and you might as well have just used clear text connections to start with. A good HTTP client should perform hostname validation for you, which is evident by something like curl or OKHTTP, for example. All of these clients will perform hostname validation without you asking for it. An SSL client, it gets a little bit more tricky. It really depends on which library is this client using. If it's a more modern library, like libpki for boring SSL, it should perform hostname validation out of the box. However, if you're linking to something like OpenSSL, I hope you've read the documentation and you know that it's not going to perform hostname validation for you. I really just want to highlight that if you're building any of these systems, it's critically important that you know what these clients are doing, because that informs what you should be doing afterwards. Just to re-highlight, Java doesn't perform hostname verification out of the box. Go, Python, and C# actually do. And if you're ever on any kind of mobile application assessment, thick client assessment, web services where there's some kind of callback, testing whether or not hostname validation is actually performed is incredibly important for you to be able to give your client some kind of security assurance. So let's move on to custom cryptography. I want to clarify that this is not someone rolling their own SSL or TLS stack. I hope that throughout this talk we've already determined that that would be absolutely insane and that there's only a handful of people on Earth who are qualified to do something like that. Rather, this is people implementing custom cryptography over and above the use of normal TLS. So the implementations that I've personally seen can range from very simple to what I would refer to as Lovecraftian horror. So a really simple one would just use AES above TLS. A more complex one would use RSA to perform key exchange and then switch to AES, a sort of pseudo TLS over TLS if you want. And the really terrible one that still gives me nightmares is all of the above, except the application happens to pick and choose which set of keys it uses depending on which set of functionality it's actually in. That's honestly an absolute nightmare to test. But I really want to highlight here that these provide absolutely no security benefit. By using this custom cryptography, if anything, you are introducing more risk into your organization, because I would make the argument that they are harmful. If I could use an analogy, I would use a rotten apple tree. I mean, you don't walk up to a rotten apple tree shaking it and expecting anything other than rotten apples to fall out of it. So just basically, what does this look like? We've got a mobile app, it sends an encrypted request, fairly simple stuff. If we were to look at something like JSON, we've got an encrypted payload. We don't know what to do with that, and now we first have to go and figure out, okay, how can we decrypt this payload? Now, in all of the cases that I've tested, this logic is embedded within the client, which makes it very easy to figure out, maybe an hour or two's worth of reverse engineering. In some cases, it's so easy, you can copy the Java code from the Android application into an IDE and just run it, and there you go, you've got your decryption routine right there and then. So we really don't want to, for every single payload that we want to submit, re-encrypt the payload by hand. That would be insane, it would take way too much time. So instead, a colleague of mine came up with this idea where basically you create a Burp plugin that sits, well, on top of Burp. And whenever the mobile application issues an encrypted request, that plugin will go decrypt the request so that it's now clear text. Now we can go and we can use Repeater, we can use Proxy, we can use Scanner, all of your favorite tools, but you're essentially interacting with the clear text version of that encrypted request. Before we send it off back to the API, we need to remember that the API expects this to be in an encrypted form, so then the plugin is responsible for re-encrypting the payload. Vice versa happens when we go from the API back to the mobile application. The encrypted response is decrypted by the plugin, but remember that the mobile client expects the response to be encrypted, so we have to re-encrypt the response as well. So this takes something like this, which we can't really work with, and turns it into something like this that looks a lot more, or easier to understand, a lot easier to understand. The QR code there is a blog post by my colleague Dylan. It's an excellent introduction into how you could structure such a Burp plugin. I think it's got an example application as well as some scaffolding. It's really the first thing that I reach for whenever we see that we need to implement some kind of plugin to handle custom cryptography. The second solution here is a very quick and dirty one, and I'll explain why in a bit. We're essentially just replacing the plugin with an intermediate API that you develop. Why I don't prefer this mechanism as much, and I'd only do it if I really don't have time to build a Burp plugin, is that you're essentially making a set of assumptions about the downstream system that you're testing. So if I could use another example, let's say that the intermediate plugin or the intermediate API is built using Flask, Python and Flask. If we're testing for something like JSON parser vulnerabilities, we are now passing that payload through the API first, which may make a different set of assumptions about the payload that we're sending as compared to the downstream system. You might even end up in situations where you're missing vulnerabilities because of those assumptions that the intercepting or intermediate API is making about your payload. So really wouldn't vouch for this unless you do not have any time left. I highly encourage everyone to look at the Burp implementation. There are other plugins like AES Killer, for example. We've never actually used that on an assessment. It just, in all the cases that we've seen custom cryptography, there's no one solution fits all. You kind of have to spend a few hours to figure out what the client is doing and what exactly needs to be encrypted. So you do have to tailor the plugin to your specific assessment. So for a summary, I just want to reiterate that where there's custom crypto, there's trouble. If there's any pen testers in the room, I'm sure you'd agree, I don't think I've ever seen a single secure implementation of this. It's always just very rough assessments that starts with a lot of initial effort, and then suddenly the vulnerabilities like rotten apples just come falling out of the tree. And then finally, I want to use just one real-world example. We've heard of situations where companies pay a lot of money for something as fancy as a WAF to essentially protect their systems. However, then they also introduce this layer of custom cryptography. And the issue with that is the WAF fundamentally needs to be able to see the clear text version of these requests and responses to provide you any kind of additional benefit. So this is just one example. I've got a few of these. But really, if you see this, please run for the hills. And then we'll be taking any questions. Thank you so much for the opportunity. I hope you guys enjoyed it.